NanoHub U, online instruction.
Hey everyone, welcome to lecture 2.8. So in the last couple of lectures, we developed the detailed formulation for S matrices. So we're now actually going to take a step back and try to understand, before we go into detailed numerical modeling, just how does S matrix compare to other types of numerical modeling in general, right? And so there are certainly a number of advantages, and I'll go over those first, but then there are also some disadvantages or challenges that we'll cover next. So first advantage of the system and approach is that, as you could see from what we did in deriving the S matrix method, we don't have to make ad hoc assumptions about our structures or make uncontrolled approximations. Instead, we're essentially taking Maxwell's equations and then rewriting them in a form in certain types of geometries. So that means that in principle, they should be very accurate and they should apply to a wide range of optical problems, especially when the system looks like it's a layered structure. Okay, and it can even have periodicity, which is really important. Another thing that's very crucial advantage is that you can potentially treat eigenmodes or high quality factor resonant modes, especially like at single frequency, because this calculation is all happening in frequency domain. When you have like a very narrow range of frequencies and you need to find the exact resonance and basically pick up sharp spectral features, then this is very good for that. And you can also treat layers that may have vastly different thicknesses. And so if you think about, say, a quantum well laser, for example, it's a perfect example because quantum well lasers themselves have very, very thin quantum well regions made out of indium gallium arsenide that may be as thick as, say, 10 nanometers. And then you can have like hundreds of microns of gallium arsenide surrounding them, but you may also even have like layer of glass or other encapsulants that could be on the order of millimeters thickness, right? So you're spanning like almost 6 orders of magnitude in terms of thickness. If you try to solve that using some other methods that we'll talk about later, and also the eigenmode solution from unit 1, then the computational time would be prohibitive. So thankfully, we don't have to use an unreasonable amount of compute time because computing propagation through very, very thin layer is pretty much the same in terms of computational time as a very, very thick layer. So that's like kind of the advantage. It equalizes those length scales without requiring us to make uncontrolled approximations. And thus, that makes it computationally tractable enough for a number of problems to just run on a single core or small machine. You don't necessarily need to have a Cray supercomputer in order to do this. So, of course, I couldn't complete the discussion without talking about some potential disadvantages of the S matrix approach. Of course, no solution method is perfect, and this is no exception. So one challenge basically for the S matrix method is if you do have like a very large number of layers, then especially if periodicity is present, sometimes it can be less reliable and slower than it would be otherwise, just because there are more interfaces and you have to construct a more complex S matrix than you would otherwise. And then second, the Fourier component associated with like having very large index contrast in the lateral direction could cause potential problems. So especially when you have metals, this is a big challenge. And so it's well known that like for certain metals and complex plasmonic systems, this may not always give highly accurate results, especially when you have a small number of plane waves. Now, of course, one approach is basically add more plane waves because there are essentially like regions or lateral features with very, very short effective wavelengths in these plasmonic structures, right? And so more wavelengths and more plane waves can capture that, but it comes at a price. And the price is basically that the scaling of this kind of problem is not good, because remember, we're trying to basically solve an eigenmode problem. And when we solve eigenmode problems, that usually has a solution time that scales like n cubed. And so when we have an n cubed solution, then that means that like if we doubled the size of the system, it would take 8 times longer to solve. And so that may not sound too bad, but imagine you try to increase the size by a factor of 20. Now you're talking about 8,000 times as much computation. So that becomes prohibitive at some point. But of course, this is, doable in some circumstances and has been done, right? So it's not necessarily a showstopper, but it does somewhat limit if you have both plasmonic structures and complex periodic structures in lateral direction and many layers. All those things combined in 3D are very challenging. And a separate but still important challenge is that if you need a very, very large number of frequencies to be solved for, and you need so it has to be basically both sharp spectral features and very broad band response at the same time, then it can be relatively slow. In those cases, something like time domain, which will be covered in the next unit, may be a better approach. In the next lecture, we'll go into more details about how we can actually make practical use of the S-matrix method.